Hi everybody. Today we're going to start in on Chapter 9. I'm talking about probability. Um, so I thought I'd start us off with a little puzzle, sort of a pretty simple thing. I've got a pile of nickels here. Not a pile, I'm not wealthy. There's some though, there's 5 of them. I'm hoping that if I plunk them down on this like, sheet in front of the webcam, you can tell the heads from the tails. These are old school nickels, so they have, uh, that's Monticello, the Virginia home place of this guy. Do you recognize him? That's Thomas Jefferson. He's the guy who wrote the Declaration of Independence, which is pretty cool. Anyway, if I kind of shake these up and flip them down all at once, there's certain outcomes that can happen. You see, in this particular one, I got 3 heads and 2 tails. I went off the screen. 3 heads and 2 tails. So let me play that again and again. There's 2 heads and 3 tails. Right? So how many different outcomes are there to this little game I'm playing? Game might be a strong word for it. What we've seen was 2 heads, 3 tails, and 3 heads, 2 tails. Is that it? No. You could have 0 heads, and that would mean 5 tails. I think it'll be a pain to write them all out, so I won't say heads and tails anymore, but there could be 1 of the heads and 4 of the tails. There can be 2 and 3, 3 and 2, and 4 and 1. Oh no, 1 more possibility. 5 heads and no tails. All right. So those are the outcomes. Would you say these are what are known as equally likely outcomes? Is it just as likely to get 5 heads? Oh, sorry, 5 heads and no tails, as it is to get 3 and 2? I think most people would say no, because it's pretty unusual for 5 heads to come up. I mean, it could happen. I'd probably sit here for a while tossing coins before it would happen, and one of them would go off the edge. How close are we? Yeah, we're right in the middle, 2 and 2, so no matter what I do with this one. Yeah, so we need to be able to count the things in a way that makes sure that the likelihood of any one of the outcomes is the same as any of the others. And there is a way to do that. Basically, don't think of these guys as being just a clump of 5 objects thrown down, but think of them as, here's the first coin, here's the second, here's the third, the fourth, and the fifth. Now, does it really change the probability if I keep them in that order? They're all in that order off screen right now. Drop that one in, then drop that one in, and then that one, and then that one, and then finally that one. I mean, physically it's a different process, but I think the way the outcomes work out would be the same. And that idea will lead you to a different way to sort of organize the outcomes in this collection. Instead of the number of heads and the number of tails, keep track of the heads or tails on every single coin. Coin 1, 2, 3, 4, and 5. That means another way to think of these outcomes is 0, 0, 0, 0, 0, 0, 0, whoops, 5 zeros. That one is 5 tails. 0, 0, 0, 1, that's 4 tails and a single head. 0, 0, 0, 1, 0. That's also 4 tails and 1 head, but it's instead of the last coin, it's the next to last coin that's got the head. Yeah. Then we would have 0, 0. Oh, what am I going to be doing with these numbers? Maybe it's clear. Every binary 5-tuple could be thought of as a outcome for heads and tails, right? The zeros would be tails, the heads would be ones. You could reverse the roles, that wouldn't matter. But so how many different binary 5 tuples have, well, let's start with the easy one, have no heads. There's just the one, right? Just this guy, where all of them are tails. So that 0 heads and 5 tails things happen once. I'm just going to count how many there are and put circles around them. How about this next one where there's 1 head and 4 tails? That would be correspond to binary tuples where they're, well, like this one and like this one, where there's a 1 in one position and everything else is 4s. And there are 5 of those. By the way, the things I've just counted, you could reverse the roles of heads and tails and count them down here. There's one way to get no tails and all heads, right? And there's 5 ways to have a single 0 in the thing and 4 1s. These guys in the middle are somewhat tougher. How about we try to construct them all? Oh, well, I don't need the coins for that. Let's do it with the binary things. 0, 0, 0, 1, 1. That's got 2 1s. And 0, 0, 1, 0, 1. That's got 2 1s. 0, 1, 0, 0, 1. That's got 2 1s. And 1, 0, 0, 0, 1. That's got 2 1s. So it's 4. No, I'm lying. It's not 4 because what else could we do? Well, these all had a 1 in the ones place, in the rightmost position. How about ones that have a 0 there? Well, maybe I wouldn't want to start with that one. But 0 there, 1 there, and maybe a 1 right next to it. Okay, that's really weak. And let's write them in a new position. 0, 0, 1, 1 with a 0 in the end. Yeah. Then let's play the same game. Just take that 1 that's on the left and push it over a little bit. But keep it the last position as 0. Oh, that was fun. Shall we do another one like that? I've taken care of things that had a 1 in the last spot or in the next to last spot. This is everything, isn't it? Oh no, maybe not quite. But still, well, wait a minute. No, I'm right. That really is all the possibilities that have a 1 in this position and 0s in the last spot. Because there's only one other 1 to place somewhere, and it's going to go in one of 3 places. All right. I'm trying to get into just enough room to fit in the next case, which would end in double O's. And it would have a 1 in the 3rd position, and then it would either have that or that. And there's one last one of these things. It's unfortunately, so I can't keep up the pattern I was trying to do, but if we had 1s here and then 3 zeros, we've got another one. So by brute force, I've got 10 of these things. So 10 that had 2 heads and 3 tails, and by the same argument that you can flip the roles of heads and tails, you've got 10 like that with 3 heads and 2 tails. All right. And you should recognize these numbers. We played with those. We saw that pattern in Pascal's triangle: 1, 5, 10, 10, 5, 1. It's really because of probability things like this that Pascal invented that triangle. Although it's handy in algebraic work too. So, how many different outcomes would you say there are doing things this way, where we think about the first coin, the second coin, the third coin, not just treating them as a clump or as a group? Well, if you add up the numbers that we got, and those are all an exhaustive list of all the possible outcomes the first way, there's 32 of them. And it makes sense, doesn't it? There were 5 coins. Each one could go heads or tails. It's like binary. How many binary 5 tuples are there? Or you can think of it as 2 choices, and there's 5 times that will make 2 choices, heads or tails. So 2 times 2 up through 2 to the 5th. So if you ask for the probabilities of these outcomes that we talked about, no heads up through 5 heads, They are the number of ways they came out divided by the number of total ways that this experiment can play out. So we have 1 out of 32 times you'll get 5 tails, pretty infrequently. But 10 out of 32 times that you'll get 2 tails. Whoops, I'm pointing at 2 heads. This would be the 2 tails, right? 10, but well, they're the same probability. 10 out of 32, that's like a third. A third of the time you're going to get 2 of one and 3 of the other. In fact, if you look at it 20 times out of 32, you'll get 2 of heads or 2 of tails, right? So that's by far the most common outcome. To have situations where you have a single head or tail, that's 5 and 5, 10. I guess that's not too bad, 30% or so. Anyway, there's some specialized language that we need to use, and I'm going to pull up a scan of the book, and then we can talk about that. I hope you'll excuse the coarseness of this scan. I probably should have redone it, but it's readable, so I think we'll be fine. This is a definition that's on the top of page 566. A sample space. It's supposed to be a bold font, so that's the thing being defined. It's the set of all possible outcomes of a random process or experiment. I like to think of it as an experiment, that we're in control. We run some process and we see what happens. An event is a subset of a sample space. So if I were to return to the example I just did of flipping 5 coins all at once, the sample space is all of these things, all of these binary 5 tuples. A particular event is some subset of them. For instance, maybe I could count all the ways that we get an even number of heads. That's the things that have an even number of ones, and we would call that an event. It's kind of a big one, but let me try to write down what E consists of. E is a set of binary tuples. The ones that have an even number of heads have either 2 heads or 4 heads. There's no other even numbers in there. Oh, wait a minute, 0 heads. All right, 0 heads would be an even number, so that's 0 heads. And then we'd have like 1, 2, 3, 1, 1. Well, I guess maybe I don't want to write out all of these, but there's a lot of these ones that have 2 1s in them. How many? We counted them before. There's 10, right? But then there's the ones that have 4 1s. Let me just say ... on the end of that. Right, but 4 1s, maybe we even have room to list all of them. I guess I kind of want to move that 0 through the pack, right? 1, 1, 0, 1, 1, and then, I guess I don't quite have enough. But how many of these are there going to be? Yeah, there's 5. So this size of this event, which you indicate by putting absolute values around it, kind of makes sense if you think about, the size of a number is its absolute value, or the size of a collection or a set. Also makes sense to use the same notation. Is 1 plus 10 plus 5, 16. Interesting. So there were 32 outcomes, and half of them, 16, have an even number of 1s. I guess there's the other half must have an odd number of 1s. Does it seem reasonable that there are the same number of even throws of the dice, they're not dice, the throws of the coins as there are odd throws of the coins? Well, there's an odd number of coins, so I'm not sure how all that makes sense, but it turns out that's a rule that actually works. In this case, our event was such that there were 16 things in it. That's the subset bit, and those 16 things are each equally likely out of 32 total things that are equally likely. Well, that's the equally likely probability formula that's written right here. You got a finite sample space. All the outcomes are the same, and you have to be careful about that. You need to make sure that you're dealing with the outcomes in such a way that they are literally equally likely to come up. E is some subset of that, an event. And then, so then you have this notion of probability. The probability of E, that's what's written here as P of E, is figure out the size of E, divide it by the size of S. The next page in the book has this diagram of all the different outcomes you can have rolling 2 dice. And the scan didn't come out very good, so I went on the web and found a image that I think does a better job of it. So we can tell the 2 dice apart in this image, which is a key to being able to think about this well. So there's a red die and a white die, but they each have the number of what are called pips on the die, going from 1 through 6. So the first column, the red die, has 1 through 6 on it. Well, actually, the second column, the red die has 1 through 6. Indeed, all the columns, the red die has 1 through 6. It's across the rows that we see 1 through 6 in the white die. And in fact, in the first row, you notice those are all, well, of course, those are all the ones where we got a 1 on the red die and various numbers on the white die. So there are different outcomes one gets when rolling a die. Usually, what you do is you count up the total number of pips. So if you have the 1 and the 1 there, by the way, that one's called Snake Eyes, which I think is cute. Snake Eyes is worth 2, right? At the far extreme, when both die come up a 6, called boxcars, you get 12. So the outcomes, in a certain sense, are 2 through 12. But are those equally likely? Well, I think you'll see, like the coin flipping thing I did a second ago. No, they're not. There's only one way to get 12. But for instance, look at 3, 1 and 2 here, or 2 and 1 there. There's 2 different ways that you can get 3. The extreme comes right across the middle diagonal here. So 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6. Those all come up to 7. And when you're playing the game of craps, they call that lucky 7. Well, it's not lucky, it's just there's more of them, right? 7 can come up in 6 different ways, whereas other numbers come up less frequently. Would you consider that each of these outcomes are equally likely? That is, Snake Eyes and boxcars are the same likelihood as, say, a 3 on both die. I think that's compelling, right? That these outcomes, as long as I can tell the dice apart, they're all the same. They have the same probability of coming up. So we have these. Wow, how many things are there here? It's a table with 6 columns and 6 rows. There's 36 outcomes, and so that's the proper denominator to use when figuring out the probabilities of dice. Now, this is a really good challenge. Give yourself I hope everybody has a pair of dice at home. There's got to be some board game that you've got at home with a pair of dice in it. Pull them out and roll them maybe 50 times. Hell, 100 if you've got enough energy. And keep track of what score you got on each of them. You should have a lot of 7s. 1/6 of the time you'll get 7s. But you should very seldom get 2s, and you should very seldom get 12s. And if it's appreciably different than that, then you probably have some crooked die on your hands. There are people who actually make die that come up with different probabilities than they should. You can adjust the shape of the die just a little bit and make it a lot more likely that 6 comes up, for instance, than 1 does. Anyway, we don't need to talk about cheating at dice. That's, I think, a great example of a probability space. Probability space there, let's think about what's in that. In an abstract way, the total space consists of pairs. So 1 and 1 was the Snake Eyes. 1 and 2 pairs. That's one of the ways to get a 3, and so on. The last thing on the list was 6 and 6. And the size of the probability space here is 36. Now, I just encountered a little disconnect between the notation I'm used to and what they do in the book. I personally would write the absolute value of S is 36. But we should probably stick with what they do in Susanna Epp's book, which is not that, but instead she writes n of S is equal to 36. I guess that sort of makes sense too. The number of the set, the cardinality of the set is what they call it. All right, so if I wanted to say the probability of E, where the event E is we get a 7, roll a 7, as it were, that set is actually a certain subset of that total group of pairs, or that total collection of pairs. There's 1 and 6, there's 2 and 5, there's 3 and 4, 4 and 3. Different from 3 and 4, right? We can tell the dice apart. There's a red die and a white die. Then 5 and 2, and finally 6 and 1. That collection is all the outcomes that are a 7. And so the cardinality of that, or the number of elements in that set, is 6. There's more numbers written down than that, but I'm talking about pairs of things. That's how many pairs there are. So that is the probability of roll a 7. Sorry, I had a problem writing that down. The probability of roll a 7 is 6 out of 36, which is 1 in 6. Not real likely. It's not like half the time you're going to get a 7, but it is certainly the most common number to come up if you're rolling dice. So we've just seen that probabilities are calculated by counting the size of the total sample space, using that as the bottom of a fraction, and then counting the size of the elements in some event, and using that as the top of the fraction. So counting is going to be huge, but we want to count without actually having to count. So there's a couple of simple principles that are going to get us down that road. That is, we'll be able to count without actually having to do the grunt work. The first principle is just counting up all the elements in a set, in a line, right? If I tell you, for instance, I was born in 1961, and then, I was 1 year old in 1962, etc. And now it's 2020. Funny, there's sort of two questions I could ask you. How old am I would be one, and the other is how many years have I lived in, which are they have slightly different answers. What I really want is how many years have I lived in? What are the number of things in this collection? And you probably think you know the answer. I think most people go, well, you take 2020 and you subtract 1961 and you get 10 minus 1, because we're borrowing, you get a 9, borrowed a 1 out of that, so it's 11 minus 6 is a 5, and then that's a 9 minus 9 is 0, and then 0. Okay, wait, I can stop because that's correct, 59. Except that's not correct. That's how old I am. Right? That's not how many numbers are in this list. And well, you can see that rather quickly, I think, by putting the numbers underneath of these guys, or pairing up with those guys, the numbers you get if you take away 1961 from everybody. You get a 0 here, you get a 1 there, and down the end at 2020, you get a 59. So, yeah, it's not just as simple as subtract. Depending on the question that was asked, you might have to subtract and then add 1. So let's turn that into a generalized fact. If we have a set, oops, I've got a red pen, not a black pen. If I have a set of contiguous integers that starts at k, and k plus 1, and so on, and it goes up till we get to n. And I ask for the n of that, how many things are in that list. It's n minus k plus 1. A quick way to think about it is subtract k from everybody, and then you'll have the list 0 through n minus k. And that has n minus k plus 1 things in it, because you're starting counting at 0. Great. So here's an example of a collection that you'd like to count, literally without counting. It's the numbers 1, 4, 7, 10, dot, 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 all the way to 121. Do you get the pattern? How are these numbers related? If you see that they're all 1 mod 3, this is 3 times 0 plus 1, this is 3 times 1 plus 1, 3 times 2 plus 1, 3 times 3 plus 1, yeah. So you can realize that there's a pattern for you. The collection of things we're looking at is things that look like 3n plus 1, where n is in, what is the range that n is in? This one was for n equals 0, right? And that's 1, and that's 2, and that's 3. What is 121? Well, I picked something that had a nice round number. That looks like 3 times 40 plus 1. So there's a number in this collection for every number in that collection. And how many numbers are in that collection? I never named this set, so let's call it S. Name the size of set S is 41. And so if you can figure out a formula for your collection, and then figure out what range the input to that formula runs over, you can count the collection. And I would probably not have the energy to sit there and literally count 41 things. So there's an amusement that people sometimes play with called the shell game. I have shells, so I have 3 coffee mugs, and you have some object. Normally it's a little tiny fluffy ball or something, but you put it under one of the cups, and then you ask the other person to keep their eye on the one that had the thing in it while you do this move. You keep going through a lot of permutations until you stop and you go, where is it? And I don't know if anybody knows where it is. I know I don't. Oh, now I know. It's right there. What makes that interesting is there's sort of more complexity there than it would appear. There are only 3 cups, but there's 6 different ways that these 3 cups can be ordered. And in general, when there's n objects, there's n factorial ways those objects can be ordered. So that's going to be an example of something we're going to count. And we're going to take away from the way we count these so-called permutations a general rule for counting. To get started, we'll look at the permutations of just 2 things. So this would be n equals 2. I guess I need a heading for this. I'm doing permutations. Of n things. So, yeah, n equals 2. There are 2 permutations. There are the 2 things left in order, or the 2 things put in reverse order. And that's all you can do with 2 things. You can either leave them set or swap them. So we'd say that set has 2 things in it. N equals 3 gets a little more interesting. That's the shell game, or sometimes people play it with cards, and then it's called 3-card Monte. But the number of the permutations, the number of ways to order 3 numbers, and without loss of generality, they're 1, 2, 3. Well, there's that one, 1, 2, 3, with the 1 first, the 2 second, and the 3 third in the normal way, right? And then there's 1 and then the 2 and the 3 could be switched. That's one way to sort of get the first couple of things. Now, that's it for ones that have a 1 in the front, because how many of them are there? Well, what remains is a permutation of two things. So it's like 1, 2, and 2, 1, except it's 2, 3, and 3, 2. Yeah. So, well, we can organize this then by what number do we see up front? First we see 1s, let's try 2s and 2 other things. Those 2 other things will be 1 and 3, and they could either be in order or they could be out of order. Yeah. And finally, we could have 3 in the first slot and 2 other things. And the 2 other things, which would be 1 and 2, could be in the natural order or in reverse. So it's kind of interesting. You build the permutations of 3 things by sort of using the permutations of 2 things. But this collection is all 6 of the permutations of 3 things. In general, there are n factorial. I hope you don't mind me abbreviating. Perms. There are n factorial perms of n objects. And so let's see where that n factorial comes from. Well, we can probably see it right here. You think of it in terms of choices. How many choices did you have for the number that went up front? Well, there's 3 numbers, right? So you had 3 choices. It was either a 1, a 2, or a 3. Once that guy's laid down, though, you now only have 2 things left to pick from. So once you laid a 1 right there, how many choices do you have for the second number? Now it could either be 2 or 3, so 2 possibilities. And finally, once you've done 1 and 2, how many choices are there for the third number? Well, no matter what the 2 things you picked were, there's only 1/3 number at that point. So you get 3 possibilities times 2 possibilities times 1 possibility. Although often some people say you have no choice, really it means you have 1 choice. You can only do 1 particular thing. That example leads to this generic thing called the multiplication principle. I figured I'd say if you happen to just watch me writing with my back turned to you. So here's the multiplication principle written out. We can run through it one word at a time. If you've got a collection of things, so some collection, and you can think of it as being constructed in k stages, and there's some number of choices in, and we'll call that n sub I. There are n(i) ways to do stage I. That is, the steps of the construction have these number of choices available at them. Then you just multiply. That's why they call it the multiplication principle. You just multiply those choices all together. There's k numbers, multiply them all, and that's how many things will be in the collection. Let me give you an example of this that's kind of trivial, but not, that's the early examples probably ought to be close to trivial. I'm going to think about all the ways that I can have face cards in poker. So what are called face cards? They consist of a suit, and the suits are, let's see, hearts and diamonds, clubs, and spades, which are usually drawn like that. These guys are colored black if you have real cards. and the other ones are colored red. So here, I'll actually make it realistic. It's red hearts, red diamonds, black spades, and black clubs. So that's what we'll have for suits. And then the other thing you have for face cards is their face value. Let's just call it their value. And if they're the face cards, then they are Jack, Queen, King, and Ace. That's typically what people count. Okay, so how many ways can I build a face card? I've got 4 choices for the suit. And then I've got, that's easy, 4 choices of value. So the multiplication rule tells me that there are 4 times 4, 16 cards. And if you've played any cards, you know that's right. 16 things that have faces on them. Except actually the ace doesn't have a face on it. I don't know why they call it a face card. Anyway, what about non-face cards? If I had non-face cards, they have, instead of those values, so let's just change this to non-face cards. The same as 4 suits, but the values are 2, 3, up through 10. Nice chance to use our previous thing. How many numbers are in the list 2 to 10? You subtract 2 from 10, you get 8, and then you remember, oh, it's one more than that. So it's 9. So the non-face cards, 4 choices of suit, 9 choices of value. 4 times 9 is 36. So if you wanted to think about, just randomly selecting a card out of the deck, 36 out of the 52 cards are in the deck are not faced cards. So that's a nice example. The probability of selecting a non-face card if you're doing one of those magic tricks and the guy says, pick a card, any card, right? The probability that you get something that doesn't have a face on it is 36 over 52. Slightly more than half. Well, I guess a fair amount more than half. Cool. The multiplication principle has a visual way of thinking about it too, which is kind of nice in certain circumstances. So let me quickly do that, and then we'll go on to the next thing, which is counting beyond just permutations. But the permutations of 1, 2, 3 can be drawn as what's called a rooted tree. So we started this is a type of graph, the kinds of graphs we talked about last week. You first have 3 branches coming away from the root, and those would be labeled 1, 2, or 3. Right? Then from each of those those nodes at the end of those lines, those vertices at the edge of those edges, you'll have double branching, each one. And those are labeled with you're thinking about this first thing as your choice of a 1 to go in front, or a 2, or a 3. We're kind of doing them all simultaneously. Once you've picked a 1, then you could have a 2 for the second number. Right? And that's, so the labels on the nodes at the end of the things to the right of 1 are 1, then 2, and then 1, then 3. After 2, you could have 2, 1, and 2, 3. And beyond 3, we would have 3, 1, and 3, 2. Those are the labels. So now, the branching beyond here is trivial. there's only one more thing, and you end up with the label 1, 2, 3 there. One more thing from there, and you get the label 1, 3, 2. We just add on the choice of things to the end of the label. 2, 1, well, this has to be 3. And this, 2, 3, the last one has to be 1. 3, 1, 2, and 3, 2, 1. So the fact that we got 6 what are known as leaves at the end of this tree is because of the branching structure. It branched 3 ways, then it branched 2 ways, and then it branched just a single way. That is, these 6 outcomes is 3 times 2 times 1, or of course 3 factorial is the other way we write. The next thing I want to look at is what are called ordered selections. Or, actually, technically these are called permutations as well, but I like to distinguish between an ordinary permutation is when you pick n things out of n. So if I call it a selection, that sort of indicates I'm talking about something slightly different. I've got n things to choose from amongst, but I'm only picking out, in order, I'm only picking k of them out. And we can count these using the multiplication principle. You see, there's n things to choose from. So the first thing you'll have is n. And then once you've picked one thing, now there's one fewer things from which to choose, right? So the next thing is n minus 1. And then n minus 2, well, it depends what value k is, but so on until we get to a number here. I don't quite know what that last number is yet, but what I do know is how many of these numbers there are. There are k of these. Why? Because we're picking k things, so I have to get the first, the second, the third, up to the kth. And if there are k things, what are the what's the value of the last one? If it's n, think. In fact, it might help us to think of this guy as n minus 0. So we've got n minus 0, n minus 1, blah, 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 up to k. Until there are k of them, what is that final value? Well, if I made it n minus k, that would be wrong, because then I would have 0 through k minus 1 things. So what am I going to put in there? It's n minus k plus 1, just like it was when we were counting ordered, when I was talking about counting how many things are in a span of numbers. You might like it better if I wrote this differently, though. Think of this as, let me just say it in here, think of it as n minus k minus 1. So we've got numbers for 0, 1, 2, all the way up to k minus 1. 0 through k minus 1 means k things. But those are the same because the minus sign distributes. Great, so I can kind of write it down, but I'd like a closed form formula for it, and we do have the ability to come up with that. Let me think about what comes next. If we were starting at n and going down, what would be the next number that would appear right here if we were continuing on? Well, this is n minus k plus 1. One smaller than that would be n minus k. So what's missing from this product is n minus k and all the numbers smaller than it. And that turns it, because of the way factorials play so nicely with cancellation, that turns this into an easy thing to compute. It's n factorial divided by n minus k factorial. This choice of this number that counts the number of ways you can choose things in order, k things out of n, is often called p of n and k. Also, you may say n capital P small k, npk like that. If you look for this number on the graphing calculator, that's the way it's denoted, npk. I personally prefer that notation, but whatever. It's malleable. Maybe I should do an example. How about if we pick 3 things out of a set of size 5? The example I'm asking is the number of ways to select 3 things. And I do mean in order. From a set of 5 things. So 1, 2, 3, 4, 5. That's a great example of this thing, and shoot, we can use the formula. We know how many it's going to be, I think, or I guess the point is to verify the formula. That is, let me just say this in parentheses, p of 5 and 3, which would be 5 factorial in the top, and then 5 minus 3 is 2 factorial in the bottom. That's 5 times 4 times 3, that's 60. I don't know if I want to write 60 things. But I can draw it for you. The first thing, we have 5 choices. From each of those first things, we'll have 4 choices. Oh, I'm going to have to cheat and go lower on the board here. And then from each one of those, we'll have 3. Okay, yeah, I'm getting tired of this. I'm not going to write them all, but you get the idea, right? How many things are there total at the end of those branches? Like this top branch would be 1 and 2 and 3. Picking the smallest number I can at each stage. The next one below that would be 1, 2, and 4. And 1, 2, and 5 would be there. Well, it kind of makes sense. So 5 times 4 times 3, and then we don't have the 2 and the 1 that would bring us to a total of, what, 120 for the number of permutations of 5 things. But for P53, just 60 things. That's kind of fun. If people have played cards, these P of whatevers are numbers that are kind of important. If you did P of 52, 5, that would be how many ways can you get an ordered selection of 5 things out of 52. Hopefully you get the 52 is the deck. 5 is what's typical in a poker hand, although some games you have more. But usually you get to only count 5 cards as the final hand that you're allowed to tally up points for. So P52-5 is how many ways the dealer can deal you a hand. Interestingly though, you can get the exact same 5 cards in a lot of different ways. In fact, how many different orders could you get the 5 cards in? There's 5 things. You can put them in 5 factorial different orderings. So this overcounts the number of hands you get by a lot, by 120. So if I took P of 52, 5, and I divided by 5 factorial, that would be the number I'd be interested in for calculating odds in poker. Right? It would be the total number of hands with no concern given to the way that you got the hand, just what are the set of 5 cards that you're looking at. This has a name, and that's called a combination rather than a permutation. So let's look at that next. So this is the kind of problem I'm talking about there. The number of ways, the number of hands that one could receive in a poker game. In poker, the N would be 52, 52 cards, and the K would be 5 cards that go into your hand. But we don't care what order the dealer handed them to us, right? The first thing people normally do when they get a hand is pick up the cards and shuffle them around until they're in an order that they like, right? I mean, you're trying to visualize what are the good hands that you have, what are the possibilities. So that presents a really interesting thing. To tell whether you're dealing with one of these things or not, an unordered selection, you ask yourself this question: does the thing remain the same if I change the order in it, right? So, somebody gives you their phone number, 857, I'm trying to remember the song, 857-5309. Anyway, there's some pop song back in the day that had a phone number in it, and this is the most commonly spoofed. I think this is it. It doesn't matter. Somebody, you're in a disco, and you guys would never go to a disco, would you? A rave, and somebody gives you their phone number, and you want to call them the next day, but you don't just write their number down in random order. You keep the order that you've got. You're not going to write it down with the 5 and the 8 switched, unless you really don't want to see this person. Then you can later pretend, oh, well, I just, no. So here order matters, right? It's a phone number. If it's 5 cards in a deck, order doesn't matter. If I have rolled 5 dice and I want to say, what is the total on the dice? Do I care which was the first dice and which was the second? Not really. So some things order matters and some things don't. And that's the kind of thing we're trying to count. When order doesn't matter, you can just choose your own order, right? If you really didn't care about the ordering of these digits, you'd say, well, there's a 0, and then there's a 1. I don't see any 2s. There's a 3. No 4s. There's a 5. No 6s. Here's a 7. There's an 8 and a 9. Well, 1, 3, 5, 7, 8, 9. I'm never going to reach this human being's phone, but that's the collection if I don't care about the order. Which brings up this weird Zen moment you have to get used to. If you see nothing but things where the order is increasing, or the order is some sort of rational thing, decreasing or increasing, whatever, if the things come in order, that probably means order didn't matter and they've just been pre-sorted for you. So watch out for that phenomenon. If you are free to move things around, then it's clearly an unordered thing. But if all you see is things in a particular order, that just means somebody else did the moving around before you. Okay, that's enough of a spiel about that. Let's think about an example of this. I want to pick 3 things out of 5. Wow, that was a weird way to write O-U-T. 3 out of 5, so what could they be? Well, I mean, I guess the smallest thing would be to see 1, 2, 3. I'm not going to do 1, 3, 2, because that would just be different by order. So all of my guys are going to be in ascending order. How about 1, 2, 4 and 1, 2, 5? There's all the things that start with a 1. Actually, those are the things that start with a 1 and then followed up with a 2. What if we skipped over 2 and we had ones that start with a 1 and then a 3? Well, there's not a lot left then. There's a 4 or a 5. Well, if we skipped over 1, had 1 and then skipped over 2 and 3 and went to 4, that would be 1, 4, 5 would be the only one like that. I think we've dealt with everything that's got a 1 up front. Let's look at the ones that have a 2 up front. I think I may have room for those down here. The smallest one would be 2, 3, 4. And then I'd see 2, 3, 5. And that's both the ones that start with 2 followed by 3. Then there's to skip 1 and go to 4, and there's only room for 5 now. And there's one more thing, which is 3, 4, 5. Now, I tried to draw these in a certain way that you would see there are 6 of those, then 3 of those, and then 1 of those. Turns out there's 10 total. So we got them. But again, I don't want to count by counting. I want to count without counting. How can we figure out this number of things without actually having to count? Well, it comes about by thinking about what we just said about ordering. There are P of n and k ordered selections. Sorry. And each unordered selection is going to occur amongst them k factorial times. Let's see if that makes sense to you. The example I just did, we got 10 combinations, they're called unordered selections of 3 things out of 5. Now, P of 5, 3, that would be 5 factorial divided by 2 factorial. That's P of 5, 3, which is, I think we did this before. 5 times 4 times 3 times 2, that's 120 divided by 2, this is 60. The number I got was 10. So why? Because this count of 60 things includes each of our unordered guys 3 factorial times. This is an overcount by a factor of 3 factorial. Which means you can just divide by 3 factorial and you'll get the right guy. And what are you going to divide by in general? K factorial. So finally, we're there. The total number of unordered selections of k things out of n, this is called C of nk, and it is P of nk divided by k factorial. Right, so let me just finish this by actually getting the 10 that I just claimed was the right number for the unordered selections of 3 things out of 5. The C of 5 comma 3 is P of nk. Okay, that's 5 factorial divided by 5 minus 3 factorial. And then dividing by k factorial, that's 3 factorial. Let me write it as timesing. So just putting the 2 fractions together, what we have is a 5 factorial in the top, and then 5 minus 3 factorial, and 3 factorial in the bottom. Okay. And the general thing, C of nk, let me just say this in general, C of n and k is equal to, it has n factorial in the top, and in the bottom, the denominator has n minus k factorial, as well as k factorial. Let's do an example of this. how about C of 10 comma 4? That would have, just plugging 10 and 4 into these locations, we'll have 10 factorial in the numerator. 10 minus 4 is 6, so 6 factorial down there, and also 4 factorial down there. Notice that the numbers that appear with factorials on them in the denominator add up to the thing in the numerator, because n minus k and k add up to n. Now, this turns out to be easier to calculate. You don't have to jump to writing out 10 factorial and then dividing by whatever the product of 6 factorial. There's a lot of canceling that'll happen. So 10 factorial over 6 factorial, that is 10 times 9 times 8 times 7. And we've already gotten rid of the 6, 5, 4, 3, 2, 1 there. And well, we do have 4, 3, 2, 1 from the 4 factorial. And usually there's lots of good stuff you can do with that. Like here, the 4 and the 2 go with that 8. And the 3 goes with one of the 3's in that 9. It's 21 times 10. Okay, it's 210. If you've been paying attention, we've seen that formula before. That's the formula for the numbers in Pascal's triangle. So these are also known as n over k, where you put the parens around. That's the binomial coefficient. I think I'm going to stop. What the? Okay, I want to do one last thing and then stop it here, and that's let's figure out the number I talked about that has relevance for people who like to gamble in poker. Well, you don't necessarily have to be gambling, playing with your friends. You could do it for just chips or something. It would be written C of 52, 5, or 52, choose 5 in the binomial coefficient notation. And that is 52 factorial divided by two things. What's 52 minus 5? I think that's 47. And then 5 factorial. Yeah. The 52 and the 47 is since the 47 is almost as big as 52, you should do all the canceling you can out of that. In fact, think about what this is going to be. It's a descending product starting at 52, and it's going to have 5 terms in it. And then 5 times 4 times 3 times 2 times 1. Kind of don't need the 1, but yeah, whatever. All right, so let's see. How about the 5 and that one turns it into a 10. And then we've got 2 times 3 times 4, that's 24, right? Oh, perfect. That leaves 2 out of that. So this number is 52 times 51 times 10 times 49 times 2. Probably should have had a calculator handy to do that. It's like 2.5 million, I think, but I'll come back and tell you. Yeah, it is equal to about 2.5 million. 2,598,960. Might as well do one probability thing while we're here. Essentially the best hand in poker, unless you have wild cards, is a thing called the royal flush, where you have 10 through ace all in the same suit. So there's only 4 of them. So if our event E is equal to getting a royal flush, the number of things in E is 4. There are 4 ways to do that. So the odds, or the probability of drawing a royal flush in poker is 4 divided by that number, which is, might as well be 0. I guess since it's in my calculator, I can tell you what this would be. 4 divided by last answer. 1.539 times 10 to the minus 6. So let's call it 1.5 with, I gotta move the decimal point 6 spots. That would be 1, 2, 3, 4, 5, 6. It's not very much. All right, so that'll be it for Monday's class. I should have another one of these posted hopefully tomorrow, which means I'll be a couple of days ahead of things. See you then.